picojoules per flop, we are all kind of limited by Moore's law. Okay, there is no magic. If anybody tells you there is any magic, I want to go see them and fall on their feet and so all optimization opportunity now is on picojoules per bit. There is at least 10x optimization opportunity on picojoules per bit on moving data and all. So that's where I think productive things are going to come. On flop, only magic like, oh, can I do 1-bit neural nets? Awesome. If you can, do everything in 1 bit or 0 bits, right? You'll be magical stuff. But other than that, there's, we are bound by Moore's law. Whatever TSMC gives us, that's the, the energy efficiency that we get. Thank you.
Robert Glory. Thank you. Now we give you Ash Vardanian. So Ash is the brilliant founder of Una, my wife project, in which he's created a faster vector search service than any I know. He's going to give a great talk about the future of his organization. Ash also is the originator of the Hardcore Hackathon. So at AGI House, we have a lot of these different threads, AI for Thought, the Hardcore Hackathon, and he's been core to making this exist. So thank him for your existence and for your attention. Ash.
Oh, thank you. It will be really hard to follow those 4 perfect talks before this one, but I actually couldn't have asked for a better segue. So the first equation that Raja was showing was about performance and generality. I will talk a little bit about performance at start and more about generality at the end. So yeah, I maintained and implemented several libraries that are open source. They do all kinds of bit swizzling hacks, or bit twiddling hacks, call them whatever you want, where you kind of shift data in different ways, interleave it, and then you can kind of in a single CPU iteration can process multiple entries of data at once, which many people know as SIMD or SWAR, SIMD within the register. And we did it for strings, and we beat the assembly of libc by a factor of 3. We did a lot of things for vector operations, but that's kind of boring at CPU side. On the GPU side, however, I think I started programming GPUs around 2009 or 10, and that was on somewhat mobile devices or smaller GPUs. And there's this sample code that I use for demonstrations and teaching for the last 5 to 10 years, where we show how different it is to program parallel reductions on different kinds of hardware, with different kinds of compilers, with different kinds of languages. And sadly, this is practically the only piece of CUDA-related software on my GitHub. And today we're going to change it. So in reality, my team and I, we've been working on a lot of very general applications of parallel hardware, one of which, about 3 years ago, we published our database engine, which is a transactional database engine that can run on a GPU. We outperformed on the CPU side the existing state-of-the-art by a factor of 10, because we like low-level programming, we don't like memory allocations, and we love assembly. But on the GPU, it was even more impressive than that. We haven't had the chance to open source it yet, but I was thinking what I can do today, maybe something more digestible than an entire database engine. And there are all those non-trivial topics that exist around CUDA that most people don't really access. So yeah, we know about those shared memory buffers, or being able to use GPU caches more effectively. But there are tricks that became more popular in the last couple of years that I would love people using today. And I wanted to enumerate some of those so that you all know where to look and what kind of documentation to search for during the day. One of those things is about low-level programming. And I realized it would be too ambitious to give a talk about PTX and SAS in a matter of 10, 20 minutes. But those are the intermediate representations in case of PTX and the low-level assembly that goes onto the GPU. You can program this directly. You don't always have to write CUDA. You don't have to come from the C++ land. Then there is a website that is among my tabs. So when I start my computer, this is the first thing I see. So I get 3 or 4 tabs that pop up. One of them is the intrinsics for x86, the SIMD intrinsics. The other one is for ARM. And the one that kind of everyone neglects, so ARM is not very popular, but CUDA is forgotten by everyone. So a lot of the logic in the GPU land, especially on NVIDIA, operates at the level of 32-bit words. but not all of the data is born 32-bit wide. So if you're dealing with FP8 or int8 representations, there are intrinsics in CUDA that you can use to access more flops per volume of data fetched, or actually I should say more flops per round of data fetching, which is probably more important here. Another thing that became popular a couple of years ago, and this is probably the most messy part of CUDA, it's cooperative groups. So CUDA has at least 3 mechanisms for scheduling. One of them is streams, the probably original one. The second one is the computational graph, or like the DAG. And the third one is cooperative groups. All of them achieve somewhat different goals, but they have kind of interleaving functionality. So if you kind of draw a Venn diagram, there's like a centerpiece where every one of them appears. Cooperative groups are arguably the most functional of those. And they also go beyond like single GPU. They allow you to schedule sometimes like multi-GPU workloads. But then the part that everyone forgets about is this, GPU direct storage. So to make GPUs more widely accessible, NVIDIA actually designed a set of additional tooling for you to be able to map persistent memory like memory from your NVMe SSD onto VRAM, which is an amazing way for you to bypass the CPU and send data directly into the GPU. So if you can work with volumes of data that are, let's say, under 80 gigabytes on the GPUs that we have today, you should look into this. Then, probably the last and the most forgotten piece of NVIDIA's ecosystem is their Rapids libraries. So Rapids, I would say, is one of the highest quality in terms of compatibility with existing Python tooling library or like set of libraries that I've ever seen. So I think I've been mentioning them over like 3 or 4 years now at different conferences. They include CuPy, which is a GPU alternative to NumPy. There is cuGraph, which is the GPU alternative to NetworkX. And there is cuDF, which is the GPU alternative to Pandas. And like, I think Pandas API is like over 100 functions. I think there's only like 2 functions that don't have full argument level compatibility with Pandas. So this is really hard to get done at this level of compatibility, and almost always across the board to get boosted performance. But the reason this matters at the CUDA hackathon is that aside from ability to write just like Python code and have it executed on the GPU using the underlying CUDA frameworks, it also includes a lot of custom stuff for you to write JIT compiled code. So this is the snippet I think I should show you, where you can essentially write heterogeneous code with extern C and then like a CUDA kernel within your Python file. And when you're prototyping new GPU code, this functionality is exceptionally handy. So you can start with the Python code, and then what I generally do, I switch to Numba, which is a Clang-based Python project, and Clang is based on Clang, and Clang is a front end for LVM. So you get all of this machinery that you can already use today to first design kernels in Python, then JIT compile them on the CPU side, and then use CuPy with the all underlying NVCC and NVC++ machinery to do the same on the GPU. And, well, you could have thought that I'm just talking here, but a couple of days ago, I decided to put my money where my mouth is, or more importantly, my time where my mouth is. So I decided to start like a very small project that can be a scratch pad for all of you. And I thought a catchy title would be Scaling Democracy with GPUs and algebraic graph theory. And what I mean by this, there's a lot of people in the Bay Area who use GPUs to scale matrix multiplications. And we all know linear algebra just works fine on GPUs. But what about all the combinatorial problems, such as voting mechanisms? And I've worked on a lot of those, especially like with the applications to graph theory and the applications of graph theory to something else. And there is an algorithm that is called the Schulze voting method, which kind of resembles the Floyd-Warshall algorithm for widest paths. And it has a structure that is similar to matrix multiplication, but has a sequential dependency in it. So over the last couple of days, I've implemented the Python version, the Numba version, and the CUDA version that still contains a bug in it. Frankly speaking, I could have titled this talk not the Scaling Democracy, but Scaling Piracy. The reason I could have done it is because Schulze method is used for voting within all kinds of pirate parties, and maybe Wikimedia Foundation, maybe Linux Foundation, I'm not sure. But I thought, I'm not really planning to testify in front of Congress this year, so scaling piracy was not really on the radar. I decided to go with scaling democracy. Today, I will be fixing some bugs in this implementation and maybe working on other combinatorial problems. But I already went ahead, and before we started today with friends from Nebius, I connected to the H100 machines that they are providing. I tested just the raw throughput of the system, and we've kind of proven that there is validity to this. So if you remove the sequential dependency from the algorithm, you can go from 20 CPU cores, that is roughly 66 seconds, to 3.6 seconds already on an H100. So this is not like pure 20x improvement in efficiency, because 20 cores is not comparable to an H100, but maybe like a 2x efficiency improvement in energy consumption or so, which is a good start. And the reason I'm emphasizing this project is because when you deal with CUDA, probably one of the first things you have to check out is CMake, which is one of my most hated things in universe. I've been writing C, C++ for 20 years. I don't know how to write CMake. So to avoid this, as you see, this project contains no CMake at all. Yeah. Thank you. I suffered for hours yesterday to avoid this. So there is one Git submodule. There is no other form of dependency management of package managers that connects TCCL, which is the bundle project of NVIDIA now for Thrust, Cobb, and their STL library. So as long as you just pull Git submodule, it works. Then you just pip install locally, and the setup py contains all the scripts to build up the CUDA kernels. It brings up the includes for all the header-only libraries that CUDA has. And there's also a benchmark in Python that compares Numba to the raw kernels. So that's it. If you need a starting point for today's project, feel free to check this out. I'm open to questions, and then we'll give the mic to the Nebius team. Thank you.
One question for Ash.
Can we get the list of those links? This is a good starting point.
Oh yeah, so if you just go to Vardanian/scaling democracy, which probably could be a good title if I run for elections or something, you will find whatever you need to get started.
You can also drop those links in the Slack.
Oh yeah, I can. I will. Perfect.